DO-178C or ED-12C contains guidance that is generally applicable to safety-critical airborne software. And CAST-32A was a position paper that had some additional considerations relevant for multi-core processors. And it contained 10 objectives which were deemed to be relevant for the certification of multi-core processors. However, this fell short of formal guidance. And so this is where AMC 2193 comes in. This is official guidance. It's an acceptable means of compliance document that's been provided by EASA. It was released earlier this year. And it's expected that the FAA in the US will release the conjugate advisory circular soon. And so what this does is it formalizes the objectives in CAST-32A into official guidance. Now, as part of the consultation process, myself and some of my colleagues at Rapita had some input into some of the modifications, some of the differences between CAST-32A and AMC 2193. So what we're going to do now is go through and look at some of the things that are the key differences between CAST-32A and AMC 2193, and look at the implications that these changes might have for your multi-core avionics projects. Now, the first key difference that we're going to look into is dynamic allocation of software. So in CAST-32A, it was encouraged that you do, the use of dynamic allocation was discouraged. So being able to allocate a piece of software or a task to run on one core or a different core was generally discouraged. Now, AMC 2193 has tightened up a little bit more on exactly what is recommended and what is not recommended. So it says that dynamic allocation features used within the scope of this AMC may rely on robust and proven limitations that lead to deterministic behavior. So actually, this is a bit looser than we expected, maybe. And it's potentially allowing, in certain limited circumstances, dynamic allocation of software. So just looking in a bit more detail about what this change means and what it does not mean. For example, if there are different modes of operation of a system, the allocation of tasks or applications to cores can differ between modes. So in my next slide, I'm going to look into this in a bit more detail with an example. It also means that if I do have a task or an application which I can schedule on more than one core within the bounds of my system architecture, whichever core this task or application is scheduled on, we still must demonstrate that it will meet its deadlines in either case. So what this does mean is that in certain circumstances, the additional flexibility of being able to dynamically allocate something to one core or another core will bring with it additional verification effort. Just to be very clear on what this change does not mean. This doesn't mean that I can dynamically choose at runtime to say, I'm going to put this task on core number N. It needs to be something which is in some sense deterministic. And this is very clear in the AMC. The other thing that it is very clear that it does not mean is that we can migrate tasks between cores depending on loading of cores at runtime. So this is something which is very commonly found in desktop operating systems as a way of optimizing average case execution time. However, it becomes very, very difficult to reason about worst case execution time when we can dynamically migrate tasks between cores. And that is not covered by this AMC. So if we look at this with an example, I have here a screenshot from our Rapitask product. So this is our product that's designed for scheduling analysis of real-time systems. And here we have some swim lanes running left to right. You can see the top set of swim lanes are annotated as belonging to core 0, a multi-core system. And the second set of these swim lanes are annotated as belonging to core 1 of our multi-core system. And you can see there are two modes here. The first mode, which is on the left side of this diagram, is maybe a mode that's active while an aircraft is on the ground. And then the mode on the right that happens at some later time is a mode which is active while the aircraft is in flight. And you notice that some of these tasks annotated in these swim lanes are flight mode tasks which appear only during flight mode, and some of them are ground mode tasks which appear only during ground mode. Now you might notice there are two swim lanes, one on course 0 and one in core 1, which annotate with big blue arrows on the right. And this is a task which executes in both ground mode and flight mode. And you note that in ground mode, so on the left, this is annotated in solid blue bars in core 0 and in hatched blue bars on core 1. And so this is Rapita telling us this is a task which is scheduled at some point on core 0 and at some point on core 1, and it's solid on core 0 because it's scheduled there. Then after the mode change, we have migrated this task from core 0 onto core 1, so it's now being shown as a solid blue bar on core 1 and a hatched blue bar on core 0. And this migration behavior that is deterministic, well-defined, is now explicitly permitted under AMC 2193. So this is some additional scheduling flexibility that is given at the schedule design stage. Again, being very clear that we must demonstrate that our task will meet its deadlines and all of its timing requirements, regardless of which of the two configurations it's scheduled in. Now, moving on to the next of the changes that we've seen from CAST-32A to AMC 2193 is simultaneous multi-threading. So in CAST-32A, this was described as hyperthreading, which is Intel's name for the generic concept. Now, for those of you who are perhaps not familiar with this, this diagram should hopefully help me explain. So on the left in this diagram, we have a multi-core system where we have two cores which are connected by a shared bus. And each core has its own execution resources. So it might have its own ALU, its own floating point unit, its own load store unit, and its own caches. It also has its own architectural state. So this is things like its context registers, for example. And so this processor, it's a multi-core processor. It can execute two threads truly simultaneously. Now on the right, we have a diagram showing a core that might support simultaneous multi-threading. And it still has, it's a single core, so it has one lot of its architectural processing resources, so things like its ALU, its load store unit, its floating point unit, but it has more than one copy of its architectural states. So it's able to support multiple virtual threads, each of which has its own context registers, for example. And this allows the processor to better optimize the use of its processing resources, but it doesn't mean that it can truly execute two things simultaneously. Now, CAST-32A recommended that applicants who are intending to use simultaneous multi-threading or hyperthreading should contact their certification authority, and it didn't go into any more detail. Now, AMC 2193 has been a little bit more clear about this, and now explicitly states that simultaneous multi-threading is not a multi-core issue and that it cannot offer any guidance. However, it also makes it clear that if you are intending to use any simultaneous multi-threading in your project, whether it's multi-core or not, you'll still need to take it into account for your ED-12C or DO-178C development. Now, the next key area that we're going to look at is the area of coprocessors. Now, in CAST-32A, there was no explicit recommendation concerning the use of coprocessors. Now, AMC 2193 has now added some explicit guidance, indeed some explicit exemption for systems where devices or cores are acting as coprocessors that are fully under control of another core. For example, a GPU whose execution is entirely under the control of a CPU core. So, a bit of analysis. What does this mean? Well, it means that a coprocessor fundamentally can be treated as a shared resource rather than perhaps as a core, given the proviso that they need to be controlled by a core rather than being autonomous. However, this does not mean that we can work around and exempt any multi-core system from AMC 2193 if we can designate one core as a master core and try and claim that the other cores are always fully under control of this master core, and therefore there can be no interference. Indeed, an additional thing that we'll come to later is that AMC 2193 is very explicit that multiple components of the same application executing under the core simultaneously can interfere with each other and should therefore be accounted for. Another thing that it does not mean is that multi-core interference related to coprocessors can be ignored when meeting AMC 2193 objectives. And we'll have a look at that in a bit more detail with the example on the next slide. So a GPU is a very commonly used coprocessor that might be used for graphics processing, graphics rendering, and may even be used for some compute. Now, if a GPU is fully under the control of an application that is executing on one of the cores, then we can treat our GPU as a coprocessor. And so what this means is our GPU is a shared resource, potentially. If more than one task or application is trying to use it at the same time, then we need to worry about contention for this GPU as a shared resource. And it also means that even if there is only one application or task that's using our GPU at a time, but it's connected via a shared bus to the CPU cores, which is the typical arrangement that we see, is that we have a GPU that might be hanging off a PCIe bus, which is attached to the main interconnect that's shared between the cores. While we may be able to make the argument that only one thing can ever use the GPU at a time, it is still connected via a shared bus, which is potentially being used by other tasks, applications, or cores at the same time. So we still need to do some interference analysis there to guarantee that the data and commands being transferred to and from the GPU are going to be able to complete within their deadlines. If our GPU is behaving autonomously and is able to, for example, start initiating transactions or raise interrupts to cores, then it does need a more thorough treatment. And generally speaking, the less autonomous we can make our GPU, the easier it will be to either make a robust argument that it's a coprocessor, or if we can't fully make that argument, the simpler it will be to demonstrate that it cannot interfere with things that are executing on the other cores. Now, we have received a couple of questions actually before this webinar, requesting some clarification on what happens if, for example, we designate different parts of a GPU to different tasks or applications that can use it simultaneously. And so I'll quickly take a couple of minutes to hopefully address that now. Now, as you can see in this nice diagram, we have a typical GPU will have several different compute units in it, each of which is able to execute a number of threads, and which will typically have some resources which are private to that compute unit. And there are, depending on the GPU manufacturer and the GPU implementation, there are several different ways that a GPU can be sliced up and shared. Now, in some cases, we see GPUs which are able to effectively fully isolate different parts of the GPU and present, as far as the rest of the processor or the rest of the hardware is concerned as 2 or more completely independent GPUs. And these might be very carefully designed such that even the cache that's on the GPU is fully partitioned, such that different banks of flash are used in order to keep them separate, and so that different memory chips are used as well. And in these cases, it might be possible to make an argument, actually, this thing is behaving as 2 completely independent GPUs, which just happen to share and interconnect to the rest of the system on chip or the rest of your multi-core system. And in this case, we might be able to make an argument that actually the shared resource here is just the bus that connects them. And then we can do some simple interference testing to make sure that despite any multi-core interference on this bus, we're still able to meet our deadlines. In other cases, there might be some software partitioning that's available. So this might be technologies like SRIOV, which can be used to partition a GPU in software to present as multiple GPUs. And in this case, it might be a bit more complicated to demonstrate that they're sufficiently independent. And we might have to start doing some interference testing to verify that tasks running in one of our GPU partitions cannot interfere with tasks running in a different GPU partition, sufficient that will make them miss their deadlines. And the final case that we might consider is where we have a system like maybe CUDA or OpenCL, which allows several different applications or tasks running on the CPU to start assigning tasks to work queues or thread groups, and leave the GPU to schedule as it sees fit. And while in general this might be a good way of getting highest average case performance, it becomes very, very difficult to reason about the worst case execution time or the different interactions that you might see between these different tasks or thread groups. So in general, for safety critical applications, we would recommend against that. Now, the next change that we're going to look at is actually quite a minor change, but it's one which, certainly from some discussions that we've had with some of our customers, is one which I think is still worth us being very clear about. And this is robust time partitioning. So in CAST-32A, there were very clear definitions for what robust resource partitioning is, which in fact is pulled straight through from DO-178C, and what robust time partitioning is. However, in the wording for MCP Software 1, it was actually potentially ambiguous about whether robust time partitioning was strictly necessary. And it was possible to read it as such that for MCP Software 1, you can take the easier verification option if you can just satisfy robust resource partitioning and have some time partitioning. So AMC 2193 has now clarified that indeed both robust time partitioning and robust resource partitioning are necessary in order to short circuit the objective and to independently verify these components. And so this is very important for IMA systems because, as I said, both CAST-32A and AMC 2193 draw their definition of robust resource partitioning directly from DO-297. So if you're interested to read more about partitioning, I will signpost you to a blog that we published on our website recently. There is a short link here. And as Nick said, we're very happy to circulate the slides after this webinar. Now, just to be very clear about this robust partitioning clarification, it is, as I said, unless both robust time partitioning and robust resource partitioning are present, applications cannot be verified separately. And just to be clear about what robust partitioning means, this does not mean that interference has to be fully mitigated. It just has to be mitigated enough that we can make some very strong claims about deadlines always being met despite any interference that might be present. So on a similar vein, this does not mean that any RTOS or hypervisor that provides some temporal or spatial partitioning facility can be automatically considered to be robust partitioning. And indeed, it doesn't mean that partitioning that is robust in one context is robust in all contexts. An example of this might be if many RTOSs and hypervisors will provide mechanisms that might partition different resources in an attempt to mitigate interference. And what we find is that actually, in general, these RTOS or hypervisor provided mitigations can be quite effective. But just because my mitigation mechanism, which is effective on, I don't know, on my T2080, using my RTOS or hypervisor, this does not necessarily mean that if we use the same RTOS or hypervisor on a different platform, maybe a Layerscape platform or something, Xilinx UltraScale Plus platform, that mechanism is automatically just as effective on a different platform. And so here I have an example of exactly what I mean here. So I've got a screenshot from my RapidTime on-target timing analysis tool. And what I have here is I've taken a task and I've executed it on, I think this is a Xilinx UltraScale Plus platform. And I've executed it with, on the 3 cores which my software is not running on. I have some RapidDemons, which are our interference generators that are DO-178C qualifiable. In this case, RapidDemons are accessing our level 2 cache. And I have measured 3 different scenarios where I have 1 RapidDemon, where I have 2 RapidDemons, when I have 3 RapidDemons. And at the bottom half of this window, you can see there is a histogram of the execution times that we've recorded for our software in these 3 different scenarios. And as you can see, as we add additional RapidDemons, the recorded execution time of our software is increasing as the interference is increasing. This is unsurprising. On the Xilinx UltraScale Plus platforms, level 2 cache is a shared resource that is shared between the application cores. But if it's the case that even in our simulated worst case, where we are generating as much interference via this interference channel as we can, if we're still not breaking our deadline, then this gives us the ability to claim that the partitioning that we have in place, while it's not completely isolating the different tasks on the different cores, it is providing sufficient mitigation that we are going to meet our deadline, provided we have sufficient engineering margin in place. The next area that we're going to look at that has been changed, and this is quite a major change, is looking at the critical configuration settings. In CAST-32A, there was an objective as MCP resource usage 2. And this objective provided guidance on the need to mitigate against the inadvertent changes to critical platform configuration settings. Now in AMC 2193, this guidance has disappeared. The objective MCP resource usage 2 still exists as a placeholder, but it's now a reserved objective. There is nothing to do for it. It just exists to help smooth the transition from CAST-32A to AMC 2193 and maintain the same numbering of different objectives. And AMC 2193 points out that actually mitigation of changes to critical configuration settings is already covered under airborne electronic hardware guidance in AMC 2152A with objective COTS 8. However, should note that just because this objective has migrated, it is still something that needs to be done. As part of AMC 2193, no, you don't need this mitigation to be in place. However, you are doing some airborne electronic hardware, you need to follow AMC 2152. And so what this doesn't mean is it's not necessary to put in any mitigation for inadvertent changes to modification of your CCS, because in order to satisfy AMC 2152, you must have this mitigation in place. And indeed, as part of the planning objectives for AMC 2193, you're required to identify these critical configuration settings, which will then feed into the mitigation as part of AMC 2152. Now, moving on, the next modification that has appeared in AMC 2193 is looking at use of simulators to simulate the behavior of multi-core processors. So CAST-32A didn't necessarily address simulation in a huge amount of detail, but it does note that simulation of interference channels is less likely to be representative compared to on-target measurement. So there was already some encouragement that on-target measurement is viewed as superior to doing some simulation. However, AMC 2193 has added to this, and there is now a clarification that simulation is also less likely to detect errors. And I guess this is a hint that a qualifiable simulator for a complex multi-core processor may actually not be possible. So I have a quick example here that should help illustrate the complexity of effectively simulating a multi-core processor. So on the left here, I have a block diagram. It's for an STM8. It's a low-power 8-bit microcontroller. Indeed, it's a very easily or readily simulatable system. It can be very deterministic. Indeed, you can calculate your execution times simply by counting instructions and adding the latencies together. I mean, as you can see, it has up to a couple of kilobytes of RAM. Indeed, most of the models will just have maybe a kilobyte or so. Very few, very simple peripherals, and a very, very simple interconnect that connects all of the components together. Now contrast this to a component on the right. So the T2080 is a multi-core processor from NXP, which quite a number of our customers are either actively using or are very interested in using for their multi-core avionics. And we have 4 cores which are capable of simultaneous multithreading. Indeed, every one of these cores has an instruction data cache, which themselves are larger than the entire memory of our simple 8-bit microcontroller. There is a very complex interconnect which is capable of supporting many simultaneously outstanding transactions, and that's capable of handling prioritization, reordering of transactions, and many, many high-speed peripherals, which are each of them capable of being bus masters and of mastering DMA transactions. And so hopefully it should be quite clear that there are many ways that different components can act in potentially non-deterministic ways, and that therefore makes it a very, very challenging system to be able to effectively and safely simulate. So this is just really highlighting the need for effective on-target measurements of the software. Now, moving on, I'm not going to go through every single tiny little typographic change that's been made between CAST-32A and AMC 2193, because there are actually quite a large number of these, and most of them have very little, if any, semantic effect upon the implications of the guidance. But there are a few other things which I would like to highlight before I go on to look at the impacts that this change has specifically for migrating projects from CAST-32A to AMC 2193. So the first of these is looking at deactivated cores. So typically, something that we see quite frequently in multi-core projects is we have customers who will come to us and say, well, for now, I only want to use a single core on my multi-core processor. So I just want to disable the other cores, and maybe down the line I might release an updated version of my product which uses the additional cores to host some additional functionality. Or indeed, that's the most effective solution to meet the requirements of the customer might be to use a multi-core processor, but just use single core activation with no intention of ever using the other cores. Now, AMC 2193 has now added some pointers straight to AMC 2152 for guidance on deactivating cores, how this should be done and how this should be demonstrated. And this is quite important. So, I mean, one example that we have from some work that we did a few years ago was where we had a dual core system and we executed some software on one core and left the second core idle. And we've measured the execution time of our software. And then we explicitly disabled the second core, so rather than leaving it idle, we turned it off completely. And then we ran our software again and we measured it again. And we found that actually our execution time had increased. And it turns out that when we disabled the second core completely, the arbitration mechanism for access to the shared bus was unable to get confirmation from the second core that it was able to access the bus. And so every time to make a bus access, it had to wait for an arbitration timeout. And so these are the sorts of issues which do need addressing when considering deactivated cores. So it is very good to see that the guidance has been updated to address that and point to some explicit guidance. The next more minor clarification or update is that AMC 2193 is now very explicit that a multi-core platform does include the platform software. So we can no longer try something which we have certainly seen our customers attempting to do is make the argument that the platform is simply the hardware, so the processor on the board that it's going to fly on. Carry out some hardware characterization on bare metal, then throw an RTOS or a hypervisor on top of it. And now it is made very, very clear that all of the platform characterization activities and the interference channel characterization activities need to be undertaken both with the final hardware and the final RTOS or hypervisor in its intended final configuration. The next modification is particularly in MCP Planning 1. It's added some guidance specifying that identification of the means of verification dependence needs to be included during the planning stage. Now, hopefully this shouldn't be a surprise. So when things need to be done with independence, these are things that we should be documenting during our planning stage. So while this is an addition to the MCP Planning 1 objective, it should be something that we are already looking at doing. Moving on, there are a couple of changes which have been made to MCP Planning 2 objective. The first is there is some clarification that the applicant should identify the hardware resources which are being used to support the AMC objectives during the planning stage. Now, those of you who are familiar with Rapita's was our CAST-32A compliance solution, and we're in the process of updating it, rebranding it to be our MAC 178 solution that Nick introduced earlier. We'll be familiar with the concept of using debug performance counters on a multi-core processor to be able to trace the resource usage of different applications to support the identification of the resources which are being used by a task or application, and to guide our analysis and verification activities. And so It's made clear now that if we are intending to use these debug counters, for example, as part of our verification process, then we need to identify these resources that we're intending to use during the planning stage. So again, I would note that this is a task that grows quite quickly as more hardware resources are being used. So it's yet another indication that the planning and the architectural design stage are very, very important, and that we should be designing software in order to minimize the use of shared resources where possible and to minimize the possible interference that we might be seeing. The other modification in MCP Planning 2 that I would like to draw your attention to is the addition of a requirement for identification of where a safety net may be required, and the identification of the mechanisms which might be used during the planning stage. Again, this is something which I hope shouldn't be a surprise. Any mitigation plan mechanisms that are planned should of course be documented. It's just making it clear really that this is design work that should be undertaken during or before the planning phase, which is where we would hope these activities are being undertaken anyway. However, we do need to be careful, for example, situations where additional need for safety net functionality might be discovered during the analysis stage. For example, during the analysis stage, we might find that there are some interference channels which might need some safety net functionality to mitigate in some way. So we do need to prepare to go back and perhaps make some additions or some modifications to our safety net design, or add some additional safety net mechanisms. And I touched upon this earlier, but we're going to come back to it and treat it a bit more fully here. AMC 2193 now highlights that if a single component has tasks split across multiple cores, then indeed it may interfere with itself. And the very, very clear implication of this is that if we are splitting a component tasks across multiple cores that are executing simultaneously, then we do need to do some testing to make sure that regardless of the alignment of these different tasks, we can still guarantee that they will meet their deadlines. And indeed, depending on the IDAL, this could be a challenging activity for meeting some of the objectives, because if you have several different tasks which are all executing simultaneously and may interfere with each other and slow each other down, this does mean that the alignment of these tasks might change. And as soon as the alignment of these tasks is changed, even by a single instruction, this can change the interaction between them significantly. And indeed, I would highlight that in some work that we have done a couple of years ago now, we demonstrated that even adding a single cycle of jitter between a couple of tasks executing simultaneously can have an order of magnitude impact upon the interference that we see between these two tasks. So moving on, I do have some take-home thoughts before we move on to have a Q&A session. And so the first of these is that fundamentally AMC 2193 does continue with the same concepts that CAST-32A introduced. There is some refinement, but there are very few very significant changes between the two. So this is actually excellent news from the perspective of a project which has started with CAST-32A and that will want to be certifying using AMC 2193 guidelines, because fundamentally a project that has started using CAST-32A should be able to relatively easily transition to 2193, with a couple of minor tweaks to account for the changes that we have discussed earlier. And finally, there are quite a few things that were either unclear or ambiguous in CAST-32A, which have now been clarified. And so again, this is good. Clarity is always good when we're trying to make robust certification arguments and build assurance cases. And so both from our perspective as a provider of solutions to help the certification process, and from the perspective of certification applicants themselves, we do have a lot more clarity now on exactly what is expected. So finally, I'd like to say a few things about how we at Rapita can help if you have a multi-core project that you're hoping to certify in ED-12C or DO-178C. So if you're already familiar with our CAST-32A compliance package, then you will already be familiar with our MAC 178 solution. It's designed to help evaluate multi-core technologies and provide the evidence that you need for certification.
Okay, so first up, we've got from Sims. Do you have any insight into the reasoning behind saying SMT is not a multi-core issue?
I mean, to be quite honest, I do mostly agree with the conclusion that SMT is not really a multi-core issue, because when we have a standard multi-core processor, it is usually the scheduling of different threads on different cores is something which we have quite a lot of control over at either an RTOS or a hypervisor level. Now, typically with an SMT system, it is logic that's baked into the silicon itself that decides exactly which threads to allow to execute, which moments using which execution units. It is very much harder to reason, both to reason about exactly what the processor will do when actually the behavior can be really quite opaque. And because we have very little control over it, it is very, very hard to exert sufficient control to be able to confidently put bounds upon what it may or may not do in terms of guaranteeing CPU time for each of the threads which it can support. So while many of the concerns which are valid for a multi-core processor may still be valid for this process that's using SMT, there are also quite a few additional concerns which would need to be addressed.
Thank you, Sam. Hope that answers your question, Sims. So I've got one from Paul here, which is, Sam, I presume just missing one deadline would then be classed as a failure. I'm not sure if that was in specifically about one slide you were going over at the time. Hopefully it makes sense.
Yes, I think I saw that question flash up out the corner of my eye as I was talking about when I had my Rapita slide up, where I had my different results when I had different numbers of interference generators shown. And as to would missing a single deadline be classed as a failure, that would depend entirely upon your requirements. So in many cases, yes, missing a single deadline might be classed as a failure. In other cases that we have seen on real high criticality systems that we've been working with, the requirements which require us to meet our deadline or to miss our deadline no more than on one occasion every however many iterations of our schedule, for example, which are a little bit more lax. It depends entirely upon the overall safety argument that we're trying to make. So generally, yes, missing a deadline is a failure, but it is going to be dependent upon the exact system that we're working with.
Thanks, Sam. Okay, next up from Sylvan, we have, does AMC 2193 distinguish multi-core processors and microcontrollers, including multi-core processors?
So I'm going to make the assumption that this question is asking about something which is maybe a very simple, very low-powered processor, maybe something like an ARM Cortex-M0, which might typically be thought of as a microprocessor rather than necessarily a fully featured processor, and whether a system which contains a couple of such fairly simple low-power processors should be treated as a multi-core processor. So AMC 2193, as indeed CAST-32A, is quite clear that the multi-core processor is a system where the processors are quite closely linked. So if I have two processors which are linked by a conventional data bus, then they are not treated as a multi-core processor. So I think the answer to your question is actually this depends very heavily upon exactly what the architecture of this multi-core microcontroller is. So if you would like to get back to us with a bit more information about exactly the sort of system you're interested in, I'd be able to give a far better qualified answer.
Thanks, Sam.
Yeah.
Hope that answers your question, Sylvan. Okay, let's go for someone else. Craig asks, can you list any platforms that have successfully completed 20193 or CAST-32A certification and are currently in operation with multi-core high integrity applications?
So to the best of our knowledge, we are aware of multi-core processors which have been successfully certified using single core activation, where all the cores but one have been deactivated. We are not currently aware of any multi-core processors which have several cores activated, which are currently in service, having gone through a full DO-178 or ED-12C certification. Though we are aware of several projects which are at various stages, indeed fairly advanced stages, through this process.
Fantastic, thanks for that. That's my understanding as well, Sam. We've got another good one from Sylvan here, which is a two-parter, and the first, so it goes: are the 10 AMC 2193 objectives dependent on DAL level? Are there any additional objectives in AMC 2193 versus CAST-32A? Okay,
so exciting multi-part question. So the easy answer to the first part of it is that yes, the AMC 2193 objectives are very dependent on DAL level. So none of these objectives are applicable for DALs D or E. So if you have a DAL D or E system, yes, you'll still probably be required to do some robustness testing, which you'll be required to do anyway, but none of the objectives of AMC 2193 are explicitly applicable. All of the objectives are applicable for DALs A and B. A couple of the objectives, specifically MCP resource usage 3, and I think, I don't say off the top of my head, I'm just going to double check. And MCP error handling 1 are both applicable to DALs A and B only, with a caveat for resource usage 3 at DAL C. Now, I think, to be perfectly honest, this is actually quite a large topic, because there is also one part of MCP software 1 which we can trade off against what we can do with MCP resource usage 3, and I think I could make a whole webinar about how best to treat IDAL-C components on a multi-core processor. But the top line, I think, here has to be that yes, things are simpler for DAL-C than for DALs A and B, but many of the objectives still apply.
Thank you.
To answer the second part of this question, are there additional objectives in AMC 2193? No, there are not. There are still the same objectives. Though, as I noted earlier, some of the changes do add explicit things which need to be done during particularly the planning stage that were not explicit in CAST-32A. So no, there are not additional objectives, but there are a few additional things that need to be done to fully satisfy some of the objectives.
That makes sense, Sam. Thank you very much. So we might be able to get through all the questions. We're going at a high rate here, so let's keep going. This one's from Adam. If the quote unquote platform also includes software, where does the boundary lie? Operating system, drivers, a support code?
I think the wording that AMC 2193 uses is that it includes platform software. I mean, if we look at this from a DO-297 IMA perspective, we would be thinking of platform software typically as the RTOS plus the drivers, and anything that is necessary to support the execution of any of the hosted applications or the hosted functionality.
Okay.
So that will be my answer.
That's great.
Now, it may be the case that in certain circumstances, you might try and make the case that some drivers might execute in user space entirely in their own partitioned off area, and therefore they should not be treated as platform software. But I think if you're interested in that sort of thing, that interests me as well. So please do come and talk to us.
Absolutely. Thanks, Sam. Okay, so just 2 to go now. Another one from Paul, which is there any indication when the FAA will follow up to EASA 2193 with the FAA's version, the AC 2193?
I would dearly like to know. I'm afraid my crystal ball can't tell me. So your guess is as good as mine. And certainly from my side, I'm working for Rapita Systems Limited in the UK. So I'm far more plugged into the European side of things. My colleagues at Rapita Systems Incorporated in the United States may have a better idea, but no, I'm afraid I can't help you there.
Okay, I don't have a crystal ball either, so we'll have to wait and see on that one, I'm afraid. Finally, last question of the day from Sylvan again. Thanks for all your questions, Sylvan. They've been great. Are the Rapita tools only on target, or are they also emulator based?
So the Rapita tools are tools that work predominantly. So this is our classic tools. They work by instrumenting source code. And now the source code, for high integrity systems, very frequently we are actually obliged to do our testing on target. And this is what the Rapita tools are best optimized for on-target testing. However, if you have an emulator that you can execute your code in, then absolutely the Rapita tools can be used to execute instrumented source code inside an emulator. So we do have customers who are using things like QEMU with our tools for doing verification activities. Now, I'd caution that for timing activities, this is typically actually quite poor. But for example, coverage or functional testing activities using Rapid Cover, Rapid Test, this might be quite appropriate.
Yep.
So the answer is yes, we can support both the use of emulators and the use of on-target measurements.
Yep, absolutely. So I guess it also depends on the stage of the project and what you're trying to achieve at that point as well.
Yes, exactly. So we also not infrequently find that we'll have customers who will start their project working on emulator to get kicked off, and then once the platform is actually prepared and ready, then migrating onto the real hardware.